The advantage of using atomistic modeling in the development of new materials is twofold. On the one hand, we have the possibility to construct a material purely virtually on a computer. We can assemble it atom by atom, like when using toy Lego blocks or pieces of a jigsaw puzzle. Having generated this material on the computer, we can simulate its physical properties using atomistic simulation methods. But we are not limited to reproducing materials which have previously been examined in detail experimentally, but we are free to think outside the box and generate completely new structures. This opens up a huge space of possibilities and a huge variety of new materials with promising properties to be discovered. The second advantage of using atomistic simulations is that we can track every atom individually. Thereby we can understand the physical and chemical processes on the atomic level. This allows us, for example, to study atom diffusion, where individual atoms move through a given crystal structure. Atom diffusion is at the origin of many processes that determine and limit the lifetime of a material. For example, there can be some reaction phase growing somewhere, or there's a phase transformation taking place. Both would alter the material properties considerably. One prominent example is that in some steels, small precipitates are required for the hardness of the steel, and these precipitates might grow during the lifetime of the steel. They do so by attracting and incorporating additional atoms from the surrounding steel matrix, and once they have grown too big, the material becomes brittle and fails. In order to prevent this to happen, it is necessary to understand the underlying mechanism, which allows us to adjust the composition and heat treatment of the steel in its development accordingly. This allows us to extend the lifetime of the material, and thereby the theoretical analysis guides the experimental efforts to design a better material.